Welcome to ViewChem, the Chemistry Animations channel. Structure and bonding. Schrödinger wave equation. Erwin Schrödinger proposed the quantum mechanical model of atom. This model considers both particle and wave nature of electron. By using the Schrödinger's wave equation, the probability of finding electron around the nucleus can be determined. The Schrödinger's wave equation is do square psi by do x square plus do square psi by do y square plus do square psi by do z square plus 8 pi square m by h square into e minus v into psi is equal to 0. In this equation, x, y, and z are Cartesian coordinates. M is the mass of the electron. E is the energy of the electron. V is the potential energy of the electron. And h is the Planck's constant. Significance of psi. Psi is the wave function. It describes the amplitude of the electron wave. The psi value may be positive or negative. Significance of psi square. It is the probability function. It explains about the probability of finding the electron around the nucleus within the limited space. The maximum probability of finding the electron around the nucleus within the limited space is called orbital. Each atomic orbital is characterized by principal quantum number, n, azimuthal quantum number, L, and magnetic quantum number, ml. Principal quantum number denotes the energy, azimuthal quantum number represents the angular momentum, while the magnetic quantum number is about the angular momentum vector component. A maximum of 2 electrons can be occupied in an orbital. Depending upon the value of azimuthal quantum number, the orbitals are named as s, L equals 0, p, L equals 1, d, L equals 2, and f, L equals 3. Number of orbitals can be calculated by the formula 2L plus 1. Value of L, and corresponding number of orbitals, are shown below. Shapes of the orbitals. F orbitals have complex shape. If the electrostatic forces of attractions between the nuclei and electrons are more than the electrostatic repulsions between the two nuclei, then a chemical bond is formed. Molecular orbital theory. Electronic structure of a molecule can be explained with the help of molecular orbital theory. F. Hood and R.S. Mulliken proposed molecular orbital theory. Linear combination of atomic orbitals. Atomic orbitals combine, either by addition or by subtraction, to form molecular orbitals. Molecular orbitals are energy states. The electrons in the molecular orbitals will be filled up based on their energies, as in the case of filling up of electrons in the atomic orbitals. Filling up of electrons in the molecular orbitals follows Aufbau's principle, that is, electrons are filled, first, into the low-energy molecular orbital, later, into the high-energy molecular orbital, and Pauli's exclusion principle, that is, a molecular orbital can hold only two electrons, with opposite spins. Atomic orbitals, of similar energies, and proper orientation, on combination, form molecular orbitals. The number of molecular orbitals formed would be equal to the number of atomic orbitals taking part in overlapping. The linear combination of atomic orbitals can give bonding molecular orbitals with relatively lower energy, denoted as sigma, pi, while the antibonding molecular orbitals have relatively higher energies, denoted as sigma star, pi star. The order of energies of molecular orbitals of simple homonuclear diatomic molecules is as follows. The above order is valid for oxygen and other heavier elements. But for boron and carbon, pi2 pi and pi2 pz have less energy than sigma 2 px. So, the order of energies of molecular orbitals for boron and carbon is differences between atomic orbitals and molecular orbitals. Atomic orbital. Molecular orbital. It is the region of maximum probability of finding the electron in an atom. It is the region of maximum probability of finding the electron in a molecule. Electron cloud around the atom forms atomic orbital. Atomic orbitals, of almost same energy, combine to form molecular orbitals. Shape of atomic orbital is determined by the type of atomic orbital, like s, p, d, and f. Shape of molecular orbital is determined by the shapes of atomic orbitals that are involved in the formation of molecular orbital. Schrödinger's wave equation is utilized to describe. Linear combination of atomic orbitals is utilized to describe. Because of the presence near a single nucleus, it is monocentric. It is polycentric because of the influence by many nuclei. Electron cloud is affected by single nucleus only. Electron cloud will be affected by at least two nuclei. Named as S, P, D, and F. Named as bonding molecular orbital and antibonding molecular orbital. Molecular orbital diagram explains the chemical bonding in accordance with the molecular orbital theory. In the following animation videos, formation of bonding molecular orbitals, addition of wave functions, and antibonding molecular orbitals, subtraction of wave functions, molecular orbital energy diagrams of hydrogen, oxygen, nitrogen, and fluorine, are presented. Combination of atomic orbitals. Atomic orbitals combine either by addition, or by subtraction, to form molecular orbitals. Let psi A and psi B are the amplitudes of the electron waves of the atoms A and B. Possibility 1. In the wave superimposition, if both waves are in phase, there takes place constructive interference. As a result, the amplitude of resulting wave increases. Possibility 2. Similarly, in the wave superimposition, if both waves are in out of phase, there takes place destructive interference. As a result, the amplitude of resulting wave decreases. Thus an antibonding molecular orbital is formed. Linear combination of atomic orbitals. Linear combination of two s orbitals. Two s orbitals can combine to give two molecular orbitals. When there is constructive interference of the two electron waves of the two s orbitals, due to addition of amplitudes, bonding molecular orbital is formed. If there is destructive interference between the two electron waves of the two s orbitals, due to subtraction of amplitudes, antibonding molecular orbital is formed. Linear combination of p orbitals results in the formation of sigma bonding and sigma anti-bonding molecular orbitals. Formation of sigma p bonding molecular orbital. Formation of sigma star p antibonding molecular orbital. Lateral combination of p orbitals can result in the formation of pi bonding and pi star antibonding molecular orbitals. Molecular orbital energy diagram of hydrogen molecule. 1s electron of a hydrogen atom. 1s electron of another hydrogen atom. The two electrons from two hydrogen atoms occupy the sigma 1's bonding molecular orbital. There are no electrons in the sigma star 1s antibonding molecular orbital. Bond order is equal to the number of electrons in the bonding molecular orbitals minus number of electrons in the antibonding molecular orbitals divided by 2. For hydrogen molecule, the bond order is 1. Hence, there exists a single bond between two hydrogen atoms. Molecular orbital energy diagram of oxygen molecule. Filling up of electrons has been shown from 2s level. 2s orbital of an oxygen atom containing 2 electrons. 2s orbital of another oxygen atom containing 2 electrons. 2 electrons are filled up in the sigma 2s bonding molecular orbital. Next, 2 electrons are filled up in the sigma star 2s antibonding molecular orbital. These are the 4 2p electrons in one oxygen atom. 4 2p electrons in another oxygen atom. Now we can observe that the 2 electrons are filled up in sigma 2pz bonding molecular orbital, 2 electrons in pi 2px bonding molecular orbital, and 2 electrons in pi 2pi bonding molecular orbital. Next, 1 electron in pi star 2px anti-bonding molecular orbital, and another electron in pi star 2py anti-bonding molecular orbital will be filled up. Bond order is equal to the number of electrons in the bonding molecular orbitals minus number of electrons in the antibonding molecular orbitals, divided by 2. So, the bond order of oxygen molecule is equal to 8 minus 4, divided by 2. That is 2. Thus there will be a double bond in the oxygen molecule. And the paramagnetic nature of oxygen can be explained on the basis of the molecular orbital theory due to the presence of 2 unpaired electrons in the pi*2p antibonding molecular orbitals. Molecular orbital energy diagram of nitrogen molecule. Shown from 2s level. 2 electrons in 2s orbital of one nitrogen atom, and 2 electrons in 2s orbital of another nitrogen atom. These 2s atomic orbitals of 2 nitrogen atoms, combine to form 2 molecular orbitals. One is lower energy sigma 2s bonding molecular orbital, and the other is high energy sigma star 2s anti-bonding molecular orbital. 2 electrons are first filled in sigma 2s bonding molecular orbital, and then into sigma star 2s anti-bonding molecular orbital. 3 unpaired electrons in 2p orbital of one nitrogen atom, and 3 unpaired electrons in 2p orbital of another nitrogen atom. These 2p atomic orbitals of 2 nitrogen atoms combine to form 6 molecular orbitals, among which the 3 lower energy bonding molecular orbitals are pi2px, pi2py and sigma 2pz. Please note that pi2px and pi2py have same energy, while sigma 2pz has slightly more energy. The other 3 high-energy antibonding molecular orbitals are pi*2px, pi*2py, and sigma 2pz. Please, again note that pi*2px and pi*2py have same energy, while sigma 2pz has slightly more energy. Among the 6 2p electrons of 2 nitrogen atoms, 4 electrons are filled first into pi2px and pi2py, and then into sigma 2pz. Bond order is equal to number of electrons in the bonding molecular orbitals minus number of electrons in the antibonding molecular orbitals divided by 2. Thus, there will be a triple bond between the 2 atoms of nitrogen in nitrogen molecule. Molecular orbital energy diagram of fluorine molecule. Electronic configuration of fluorine is 1s2, 2s2, 2p5. Molecular orbital energy diagram of fluorine is shown from 2s level. 2 electrons in 2s orbital of one fluorine atom, and 2 electrons in 2s orbital of another fluorine atom. These 2s atomic orbitals of 2 fluorine atoms combine to form 2 molecular orbitals. One is lower energy sigma 2s bonding molecular orbital, and the other is higher energy sigma 2s anti-bonding molecular orbital. 2 electrons are first filled in sigma 2s bonding molecular orbital, and then into sigma 2s anti-bonding molecular orbital. There will be 5 electrons in the 2p orbital of each fluorine atom. These 2p orbitals of 2 fluorine atoms combine to form 6 molecular orbitals, among which the 3 lower energy bonding molecular orbitals are sigma 2px, pi2py, and pi2pz. Please note that pi2py and pi2pz have same energy, while sigma 2px has slightly lesser energy. The other 3 high-energy antibonding molecular orbitals are pi*2py, pi*2pz, and sigma 2px. Please again note that pi*2py and pi star 2pz, have same energy, but sigma star 2px has slightly more energy than pi star 2py and pi star 2pz. Among the 10 2p electrons of two fluorine atoms, 2 electrons are first filled into sigma 2px bonding molecular orbital, then 4 electrons into pi 2py and pi 2pz bonding molecular orbitals. Next, the remaining 4 electrons are filled up into pi star 2py and pi star 2pz anti-bonding molecular orbitals. Bond order is equal to number of electrons in the bonding molecular orbitals minus number of electrons in the antibonding molecular orbitals divided by 2. Thus, there will be a single bond between two fluorine atoms in the fluorine molecule. Thanks for watching. Please like, subscribe and share.